Test, test. Okay. Good evening, everyone. So, dear member, distinguished guests, and all ladies and gentlemen, first of all, Happy Chinese New Year. And my name is Warapat. I'm one of the SPE Board of Directors for the Thailand section, and I will be your MC for tonight. So, on behalf of SPE Board of Directors, I would like to welcome you all to SPE Thailand monthly technical meeting for the month of February. This month we will have the interesting topic from the SPE distinguished lecturer about during automation. And thank you for being here tonight with us. And we're very happy to see all the familiar faces in our event. Also, please welcome our student. For the student, please raise your hand. Thank you very much. And thank you all for joining us tonight. So before we continue with the agenda, please take note for the safety announcement. There is no emergency drill for tonight, so in case of the alarm goes off, please be calm and follow the sign toward the designated area marked by the hotel. And here is the agenda for tonight. We will start with the section information announcement and the speaker introduction. And then the program share, we introduce the speaker. We're gonna have a presentation followed by some Q&A and the closing remark. And lastly will be the lucky draw. And for the section announcement, so SPE Thailand had been established in 1980 as a non-profit organization and proudly represent over 1,000 professional and student members from diverse disciplines across the upstream petroleum industry. Our mission is to promote the technical knowledge sharing in the professional development and community building to ensure the sustainable the future of exploration and production in Thailand industry. And we actively organize technical monthly meeting and the social event that encourage the networking and exchanging the technical idea to keep the industry community active. These 48 company as the logo show on the slide are the sponsors who kindly support us for our technical monthly program for the season of 2025 to 2026. And for any of you who may have just joined the event tonight and you would like to see your company logo here, please reach out to us. The season just have begun and we have many months left that we can have your company logo to present to the community. And we really appreciate your support and of course that the society needs you. For the section membership status, Thailand section valid membership as of end of January this year is 527. It's still less than last month in December last year. And this combining between 302 professional member and 225 student member from 4 chapters at Chulalongkorn University, Suranari, Prince of Songkla and Chiang Mai University. So may I remind you that please check to renew your membership status and please invite your colleague to join our SPE community and join our monthly technical meeting to get the update and insightful information within our industry. So please let me remind you that SPE Thailand is one of the largest professional oil and gas organization in the region where you can regularly engage in a professional venue but a relaxing environment. There are plenty of the reasons that you should maintain the valid membership for the SPE and even more the reason to join for the event. I will not go through all these as you can see on the screen, but worth mentioning that the key benefit of belonging to one of the most active SPE section in the Asia Pacific region are the regular opportunity that the network share the knowledge and socialize with the peer in the same interest in our industry. And ladies and gentlemen, we will now move on to the main presentation. And may I please invite Kun Kasian, our SPE Thailand program chairperson, represent upfront to introduce our speaker.
Okay, thank you, Ui. Thank you very much. Good job, the SMC. Okay, for those who do not know me, my name is Kasi and I'm the SPE program chair. And along with Kun Surachai and a few other chairs who may not be here today, um, I heard that we tally around 50 to 60 people in the room tonight. There's a lot of people sitting in the back. There's a lot of room available in the front. If you cannot see, because the slides over there may be smaller, you can come sit here in the front as well. Students can come. Don't worry. We're not bite. We'll just bark. All right. Okay. Without any further ado, let me do the speaker introductions. Okay. All right, so our distinguished lecturer tonight is a data science lead at Corva with a strong background in petroleum engineering and PhD from the University of Tulsa. At Corva, she leads the research and development of drilling automation projects, including the awards-winning closed-loop drilling automation project, which earned the Best Drilling Technology Award at the Gulf Energy Excellence Award in 2024. The speaker has played a pivotal role in advancing cutting edge drilling technologies, collaborating with major oil and gas operators, and contributing to numerous technical papers. A committee member and a session chair of the SPEIADC Drilling Conference. Speaker contributes to shaping technical sessions and discussion on key industry topics. She frequently shares her expertise through webinars and technical presentation at prominent global conference, establishing herself as a recognized leader in the field. Ladies and gentlemen, please warm welcome our distinguished lecturer for tonight, Miss Kriti Singh from Corva AI.
Good evening, everyone, and thank you so much for the introduction. Um, right. So, I would like to begin with thanking the SPE Distinguished Lecturer Committee for selecting me and providing this opportunity to come all the way from Houston, Texas to Southeast Asia. I'm from India, but since I live in US, I don't get to visit this part often. So I'm grateful for this opportunity. I know it takes a lot of planning and organizing, and it looks amazing. Thank you all for coming out tonight. I'd also like to thank contributions from Offshore Europe and AI Amy for supporting the distinguished lecture program. The topic today is self-driving rigs, navigating the paths to closed-loop drilling automation. It started with an internship project that I started working on after I graduated with my PhD in 2018, but we have come a long way. There's been a series of SPE published publications and a lot of collaborations with rig contractors that has led to this technology. And now it's been commercially used, and we have written some case studies on 100 wells that have been drilled with this technology, and it's only gone up now. So I'm excited to share my findings and experiences along the way, and open to your feedback and questions tonight. Okay, so before we begin, I'd like to start with a fun quiz. So does anyone here know or can guess when was the first time that the idea of a self-driving vehicle was first thought of by any human being? Like any guesses? 1950s? Any other guesses? Nine. What's that? 2000? Okay, so when I was doing my research on this, I found out that it was actually 500 years ago in the 15th century that Leonardo da Vinci first proposed this idea of a self-propelled cart. And the idea was that it should be used without any manual intervention in theatrical use. So there were pictures of the drawing of the cart, which was then like a prototype was developed by some students, which was then uh, presented in a museum in Florence, and it worked exactly that how he had imagined. And fast forward today, we live in a world where a self-driving car is no longer a science fiction; it's become an everyday reality. I drive a self-driving car every day to work, and it's been a significant improvement in quality of life because there's less fatigue. There's like you come back from work feeling more productive, and obvious there less. For me, it has been an improvement, and so the idea of a self-driving rig would be very similar. Like you'll have a drilling program when you that you'd provide to the rig, and the rig would be able to drill the well with minimal human intervention, so that there is less human error, more health and safety of and more productivity. So that's the idea of self-driving rig. And this is the agenda. So we first understand the problem statement, why we want to automate drilling. We look at some examples from other industries and where we stand in autonomous drilling today. And then I'll go into the specific of closed loop drilling optimization technique and present some case studies, and then we can have some questions and discussions. Okay, so to understand the current process, we have about 1,500 global rigs today, approximately. And on each rig, there are four different drillers, four different company men, and they have to make these human interactions. So they have to set targets, set points in the auto driller that, okay, like looking at real time data, this should be the ideal weight on bit that they drill with, or so they have to be constantly aware of all this data coming in and make these decisions in real time. So and then we are drilling through hundreds of different formations using different tools. So the main question is, how can we achieve consistency in these drilling operations? So the main drivers for drilling automation in recent years has been ever since the pandemic, we have not seen the rig count go up again as much. The rig count remains the same, but we are drilling more wells. The complexity of wells has also increased. Especially in the US, it's become common to see wells that are 30,000 feet long. So we can imagine that the complexity is much higher. And there is a pressure to give consistent improvements delivery. And we are getting terabytes of data per well. And without technology and automation, it's difficult to use that data to make decisions. And the biggest thing that the drilling automation can help is bridging the knowledge gap. So, on the same rig in the day crew, there may be a driller who has decades of experience, whereas in the night time, the driller may be relatively new. So, how do we bridge that gap in these two drillers? So, if we have an automation technology, the technology can learn from the best drillers that can be used by the new driller. And so that really helps bridge the gap. And then there is health, safety, environment. Where, I mean, the drillers have 12 hours long work shift. So if they are constantly looking at these real time data and making decisions, then there is more fatigue and there may be more chances of human error. Whereas if we have automation, then the drillers can be freed. It's not that they should be like there's no need for the driller anymore. They're still required, but they can be more productive and they can focus more on critical tasks like well control operations and preventing kick and things like that. Okay, so looking at autonomous operations across different industries. So one example is aviation industry. We have seen the autopilot now. It is responsible for 90% of the flight time, and the pilot is still there, but only to oversee critical issues. But it significantly reduces chances of human error. And also, we are increasingly seeing the adoption of automation in manufacturing, farming, agriculture, where again, the idea is to reduce human error and automate repetitive tasks to get precision and efficiency. This is the progress of autonomous drilling and where we stand in this journey. So initially, all the operations were human operated. So even like things like making a pipe connection, which was a very dangerous task. We would hear things about drillers losing their even. I mean, a lot of accidents would happen, and then there came assisted softwares where the driller would be provided with some assistance, but a lot of decisions still depends to be done manually. And then then automation of, for example, making pipe connection is now completely automated for most of the rigs. Then there is single workflow autonomy. So in drilling, there are different processes. So we at a particular time, we may want to focus more on directional drilling, where tool face alignment is the key, or there could be slide drilling, again, like where direction is more important than drilling faster. And then there is rotary, on bottom rotary drilling, where everything is aligned and you just want to drill ahead in the well. So that is a single workflow that you want to automate individually. And then the next step would be for all of this to come together. So one decision influences the other. When we do on bottom rotary drilling, we have to be mindful that we don't deviate from the planned direction. So that's where the connection comes in. And then finally, we should move towards full autonomy, which would be the self-driving rig, where basically the rig has a brain of its own and it would be able to drill the complete well. There'd be orchestrated coordination between all these different drilling processes. So going into the specific closed loop drilling optimization, which is focused more on bottom rotary drilling. And the goal when you're on bottom rotary drilling, the goal is to drill as fast as possible because drilling is expensive, and that's where you make up most of your time. So just to cover some basics of drilling, ROP is rate of penetration, which is the speed of drilling. So how fast you are drilling. And it depends on a lot of parameters, but there are few that you can control in real time to get fast ROP. So one is the weight on bit, that is the weight that you apply to the bit directly. And then there is rotary RPM, that is how fast you're turning the bit to cut the rock. And then there are other parameters like flow rate and differential pressure. So in a typical auto driller, which is the hardware that controls this drilling, there are 4 different set points that you can set. So we have the weight on bit, we have the rotary RPM, the diff pressure, and ROP, which is like an output for this. But you have to set a certain value as a set point that the auto driller chases to drill that fast. But the question is uh, basically how, like, what would be the ideal set of these parameters that should be provided as a set point in the auto driller to get your optimum ROP, and that is the problem that we are trying to solve. So this is the whole data flow of the closed loop automation. We have the data coming in from the rig in real time, and that gets consumed via a cloud. Yeah, a lot of data, a lot of this real time data gets processed. And then we have a machine learning model which predicts ROP in real time as a function of this data. And then there is a ROP optimizer, which is using the machine learning model to do a heat map search of what is the best combination of parameters at a particular time. And I will go into more details of that later. And then once all these four values are identified, that this should be the weight on bed, diff, RPM, and ROP, then these are directly sent via cloud to the human interface machine of the rig contractor itself. So basically, what happens is once a pipe connection is made, and then you are starting to drill 90 feet of the stand with on bottom rotary drilling, then in this entire process, the driller is now out of the loop, and all the data gets processed via cloud, and this analysis is done, and then it is sent directly via cloud again to the rig. So that is the closed loop automation, where now the driller can just observe and monitor other operations rather than having to decide, okay, now like what parameters should I send. This is just to give an idea of the path to get to where it is today. The first step was to develop a machine learning model to predict ROP in real time. So we have all this data coming in through WITSML. Then we also have other data like the BHA information, mud data, directional information. So all of these input parameters give the ROP in real time. So first step was just to build that machine learning model, which was published in 2019. And then over the years, there were a lot of feasibility testing done with operators to see if it works in theory. I mean, it's always easy to have a ML model working on paper, but then how practical it is on the field, it's important to validate that as well. And once we were confident that the machine learning predictions are accurate and work as expected, then the next step was to integrate with the rig contractor to develop this closed loop automation. And a learning curve here, which is something new for the industry, is that all these different service providers, like a a SaaS company, a rig provider, operator. So instead of working in silos, everyone's coming together, and whoever is expert in their own field is able to contribute and work on a collaborative solution to get this closed loop automation. Because if everyone tries to build from scratch, then it takes more time and it's more difficult. So that was a big learning. So for the machine learning model, in 2019 when we started, we used about 50 wells to train a particular model in one basin. So this was in the West Texas Permian Basin. And 45 wells were used for training, and 5 wells were held out as blind wells for validating. And MAPE, which is the mean absolute percentage error, which is the predicted value versus the actual value, and then you take the difference between the two and see what the percentage accuracy is, which was always more than 85%, or the error was less than 15%. And these are all the input parameters that were used for the model. And there were some engineered features as well. For example, a lagged MSE, which is lagged mechanical specific energy, was used as a proxy for formation strength. So the ML model that is used is a simple multivariate regression model. But a lot of input features are domain specific engineered features which help us to get the results and accuracy. And then so we realized that building the one model took a lot of time to download the data and do all the data wrangling and cleaning the data, making it more structured. So it was important to automate this process. And then now it's very easy to, like, if you want to train a model for a new basin, then you would just run this pipeline which downloads all the data in parallel, and then it's able to automate all the data wrangling process and create a new model for a specific basin. This is the ROP optimization heat map. So what it's doing is, so this black box is basically the limits constraints of the search that is provided typically by the operator or the company man. So they can specify that we don't want to the RPM search rate should be between 40 and 75, for example. Diff pressure in case of a PDM motor, or a weight on bit, so it's a 3D heat map where there is weight on bit as well. So all these limits are provided, which are the operational constraints that is in the that so it's pre-planned before the well is drilled. And then within those constraints in a particular formation, it the machine learning model is predicting ROP in real time, and then it's able to do the predictions for a combination of all these parameters, and then it finds the one where we get the minimum value of there's a full equation that it optimizes. And we also filter out the data that is correlated with high dysfunction recently. For if there is a combination of data that was correlated with high vibration or high stick slip, then it is filtered out so that we don't create those dysfunctions again. So finally, we for the starred cell is the one that it picks as the best combination of weight on bit and RPM diff, and the predicted ROP that should be set as target values for the auto driller. Okay, so this is the overview of the technology, and then the next step was to close the loop. So we work with the rig contractor to work with their API. So we get the data from the data provider, get it into the software, do all this analysis, and then send it back to the rig operator. And so the next step was to go to the rig and present this technology and um, work with them. So we spent a couple of days there to see how it's working and what results the drillers were expecting to see. And we got a lot of feedback from them that we went back and took as iterations into the software and redeployed. And this was the result from the pilot phase, like the very initial rollout, where we have in green, we have the sections where it was drilled with automation on, and blue is where it's off. And immediately we can see that there is an improvement in ROP of about 25% with automation on as compared to automation off. And then as the drillers drill more and more with automation on, the utilization went up, their confidence in the technology went up. So we could see more and more, like very few sections where it was turned off and it would just run like it became a mechanical thing that they would just, like, once the connection is made, they would turn this on and it would drill 90 feet and complete the stand. And uh, it was left turned on for a long time. Okay, so there were so the next step, once after the pilot phase, the next step is to do a scale up and deploy to more rigs. That came with some challenges. There were technology hurdles because this is a cloud to cloud connection. There's no edge device installed on the rig. So anytime there is a network outage, that would be a problem. And so there were some solutions for that, like having backup um, connection, for example. And these days, network like Starlink is extremely powerful. So that was deployed to a lot of the rigs in West Texas. And then there are some economic barriers, like some operators would question, why, what is the ROI of this investment? And they're already paying the rig crew and the drillers. So what's the need for paying for this additional technology? So there had to be like the solution for all that was to have like define clear goals and success metrics to show what the value is and the ROI is. And also in keeping the people, the end user in the loop was very important and valuable, because like you can develop something in a shell, in a silo in R&D, but is that very useful on the rig? Maybe not. And like you have to have a communication flow with the rig to understand what really helps them enhance their process, and then you integrate those ideas into the technology, and that really helped with scaling up. So it the first pilot was done in 2023, and over 2 years it was run or and tested in different fields. So we tested on Eagle Ford, Delaware, Bakken, which are some of the three main basins of US. And so last year in Norway at the SPIDC conference, we published a case study where the results from 100 wells were analyzed and presented. So for this, we use days versus depth comparison. So the wells in blue are the ones which were drilled with automation on for more than 75% utilization, and the reds are one with turned off. And the analysis was that with automation on, it would drill with comparable to the average drillers or better than them. And most importantly, what it helped was to reduce the number of interactions that the driller had to make with the auto driller or the human machine interface. So in manual drilling, they do about 250 interactions every 1,000 feet, whereas with the automation, you just have to probably change the limits in the roadmap. And it was as few as 3 interactions per 1,000 feet. And in general, as the utilization increase, for example, here it's 87%, the interactions was even fewer. Now, another important thing is we like when we talk about the KPI, we just don't want to drill as fast as possible. ROP is not the only metric. The key thing is to like days versus depth was a good KPI because that shows the total time that it took to drill the well. So if we want to make sure that we are not adding more non-productive time and more bit trips in the process, so we also analyze that we are not adding more bit trips when we use automation on. And in general, the bit run either remained the same or there was a slight decrease in trend as well with automation on. So this is a summary of the results. In Delaware, we saw a significant improvement in ROP. Bakken lateral, there was a slight improvement, but intermediate with manual drilling, they were actually faster because with automation, they would put more conservative limits, whereas when they were drilling manually, they would even push higher. So in some cases, we saw that as well. They were already an efficient, like the 90 percentile driller performance. And there was a significant improvement in Eagle Ford intermediate. Other thing that so this was the initial like first layer of this closed loop automation where we do the ROP optimization. But then as we started to work more and more with the rig, there was a need for doing more things. Like, for example, there is this tool joint dysfunction that happens every time the tool joint passes through the RCD. There is a hang up which causes this kind of dysfunction. So there is a systematic drop in ROP. And the like one of the major operators, they have published mitigation procedure for this, which is to increase the weight on bit set point in the auto driller every time they anticipate the tool joint passing through RCD. So the instructions or the procedure is for the driller to pay attention whenever the block height is approaching that like it's getting close to RCD, and then you have to manually adjust these set points. And you can imagine how hard, like if you're drilling with 400 500 feet like in the back end, you drill so fast that it's impossible for a human being to pay attention and increase or make all these adjustments 3 times in a stand. So that's where something like automation is very helpful, because it would do this procedure in a systematic fashion and it would prevent these ROP drops, because otherwise these ROP can cause a lot of dysfunction. Like it could cause backward whirling, it could cause vibration, which can cause tool damage. So, with automation, we can improve the tool life as well. And then this was very common. You see these ROP sawtoothing, which is the ROP goes almost to zero and then it goes back up. And this happens if the diff pressure the diff pressure limit in auto driller, like whenever the actual diff would be close to the diff pressure set point, it would always cause this ROP to drop. And that's just how the PID is set up for the auto driller. So you have to be careful that the set points that you send are not breaching the headroom for this to happen. So there are algorithms built inside this automation technology that would prevent this as well. Okay, so we are getting close to the end of the presentation. Just to summarize, what is the goal? The goal is to automate repetitive tasks. So there is less fatigue for the drillers and there is an increase in efficiency. We are using we have a lot of access to data in real time now, and we are leveraging that using machine learning to make decisions in real time and assist the driller. And that's the future that we would like. Right now this is just on bottom rotary drilling, but we have similar automation for slide drilling and directional control, and ultimately all of this needs to work together to have a complete self-driving rig. Okay, just a interesting data that I came across, the technology adoption trends. So we can see that in the early 1900s, there was a very slow, there was some resistance to technology. So telephone took about 60, 70 years to reach peak utilization. But as we go closer to 2005, we see that there is a rapid adoption of technology. And now we are living in a fast pace AI, LLM, like it's hard to keep up with the pace. So we are definitely there is a need to adopt AI automation as fast as possible, and oil and gas should lead the way. So that's the message that I wanted to send. And thank you all for coming. This is the QR code for sharing your feedback. I appreciate your attention and open to questions now. Thank you.
Okay, if you have a question, let us know. And before asking, please let us know your name and where you're from. Then you can ask the questions. Okay.
So, I'm Ben Sherry with Biggest Lab. I'm a AI developer. You said that the compute engine was not on the rig with the rig. Is that necessary? Is there a reason why you can't have the device there with the rig?
Yeah, we thought about that, but the problem, like we wanted to do uh, so every time, like if there is an edge device, then there would be a need to go to a remote location on a rig and install that device, which is like extra piece of hardware that you want to first develop and then install in on every rig. Whereas now, if you want to enable this technology, then it can be done, like for example, in during their downtime, it can be done with a few line of code and testing within half an hour. So it's just the ease of things.
Okay, so it's not an issue of power or size of the computer. It's just an issue of deployment.
Yeah.
Thank you.
Okay, so my name is Chitiwat. I'm from Chulalongkorn University. So I want to ask about the training method that you use because you said that you use 50 wells data, right?
Yes.
Yeah, so I think it's not that much data for model. So I just want to know that what the technique that you use to train such a high accuracy model.
Well, 50 wells is, I mean, it's enough data. We did not use deep learning models. We use multivariate regression models, which for that 50 seemed to be like we got good accuracy with that. And I guess just the techniques w- the main when we were training the model, the main it was very important to have a good interpretability of the model. Like with something like deep learning, it's more of a black box model, so you don't know which are the most important input features. I mean, there is a way to interpret that, but still the interpretability is low. Whereas for machine learning, for multivariate regression models, you can get a pretty good idea of what are the like high input features. So when we were validating, it was important to have these controllable parameters like weight on bit is what you can like change in real time to actually optimize your ROP. So that should be an important feature in your model. So we use techniques like that to in our model rather than focusing on having a large data set or large deep learning, using more of domain knowledge to drive decisions.
Thank you very much.
Thank you for the question.
Any more questions? Saw a lot of drillers.
Right, Pagon from BTTP. Um, I think you might have been asked about this a lot, right? But I'm gonna go anyway. How can you tell if your RP is already optimized? The thing is, you have your data, right? You collect the data, and then you determine, okay, this is the RP. You train your model. You get all these nice metrics, MSE, MAE, and whatnot, right? All this is based on the fact that you trust your RP value to train your model. And from that moment on, after you finish your training your model, everything else depends on those data set, right? So you assume that you can trust that data set.
Mhm.
In reality, it could be, several things combined and you get that ROP.
Mhm.
I'm not sure if I confuse you, but
No, I
yeah,
understand your question.
yeah.
So, mm, so we train a static model where the goal is that it has this mathematical equation of what are the input parameters and this is the ROP. But we also have some logic to fine tune or calibrate the model in real time using real well data. So it's able to always like uh, keep up with new data. So it's not like a static model. There is some in-well training as well.
The question was, how do you trust your ROP?
Yeah. So we have this predicted versus actual. That's one level of validation. Then I think what you're trying to
One of the timeline you put on there, yeah. Yeah. Sorry. Continue.
So
There was a slide that you showed that it
yeah,
started from 2019, I think,
yeah.
and then you keep fine tuning, you keep adding more data and validate it,
Mhm.
right?
Yeah. And I guess so that is just for the machine learning model itself, that making sure that the accuracy is high, and we have these metrics in real time as well, that the model accuracies should always be high to look at the data. And then whenever we drill a new like every few months, like 3 months or 6 months, we again test it on the new wells, and then we do a full shadow test mode to run it against the wells that have been drilled recently to validate that the wells are working, sorry, the model is still accurate.
Right. I'm sorry, but I still don't get the picture. For example, right, I'm not sure about the unit per se, I'm not a driller, right? But let's say you found the optimized value from your data. You say, okay, it's 10, let's say, meter per hour, for example,
Okay.
right? 10 meter per example. In reality, you might it could have been better. It could have been faster.
Mm.
It could have been 15. But the only data you have says 10. And that's it. Your model trusts on 10.
Mhm.
Right? How can you determine it's not going, it can go up to 15, for example?
Okay.
That's my question.
Okay. So, in reality, we a lot of so machine learning model is just one part, but a lot depends on the roadmap or the constraints that are put on the model, right?
Like bit
So
type,
the
weight on bit,
weight on bit,
your palm or whatnot.
right?
Yeah.
So weight on bit is basically what, for example, if a company man says that we want to drill with 45 weight on bit, right? So the goal would be to test like for 45, what is the ROP set point? And ideally, they should be able to drill with 45 weight on bit. So that's how we are able to say that, okay, like they are getting the
No
performance
other
that they want.
constraints.
Yes.
This is your best bet
Yeah.
number.
Yeah. With while avoiding all the dysfunctions.
Mm.
Yeah.
Okay.
The kind of dysfunctions that I like gave some examples of.
Mm.
So it tries to manage. So sometimes it may not be the max ROP. There has to be, for example, a little headroom
Mm.
to create that diff pressure headroom so that
Yeah.
it's not conflicting with different parameters.
Right.
But ultimately there has to be one parameter that you are able to fully achieve, that you want to drill with that as your constraint, and that's the validation for the model. Yeah.
Thank you. Thank you.
Hi. Um, good good evening, everyone, and thanks for the very nice presentation. It's quite interesting. I have a question on how do you manage exceptions, or like during the drilling when it's going on, if the and if you see something, if the model sees something which is off, like maybe you're getting a kick, can it? I mean, can it trigger something, or how does it work?
So as of now, the model itself does not, but we're working towards having these different capabilities tied in. So there is always, so there is a optimization mode, and then there is a monitoring or situational awareness mode. So the in hierarchy, always if there is a dysfunction or there's some anomaly, then that takes over. Like we don't care about ROP optimization at that time. For example, if there is this tool joint mitigation or auto driller dysfunction, then we want to make the system stable first. And similarly, like for kick detection, a different team is working on this the logic for kick detection, and it would say that, oh, like like this is a critical situation, and there will be an alert sent out. And again, like we are not at the stage where everything is automated to take the corrective action, but for now there is situational awareness, and then ultimately it should be automated as well. So that's the goal.
Okay, thanks.
Thank
And
you.
maybe the one thing which we were discussing just before is how do you see this moving with the new LLM and the new things which is coming up?
Yeah. So for LLM, from what we in our experience, how it's helping is just the speed of new software development, right? Like now, with the help of agent like Claude and Codex, it's so easy to write new code, and the pace with which you can, for example, uh, we initially developed these four types of dysfunction, say like stick slip, auto driller dysfunction, and two others. But there are 10 others, other kind of dysfunction, and what should be the mitigation that we need to implement. So with the help of this agentic coding, we can just provide the definition. Like any somebody who does not know coding can also code. Like basically they can provide the definition, the agent would write the code, and you can deploy fast. So it's just the speed is going to be enormous with the help of LLM. And of course, like this is a complex technology, right? So if earlier every time there was something go wrong, they would reach out to us like R&D, oh, what's happening, we don't understand. But now like you can train the for, again, like agents to understand, like go through the whole code repository, understand what is happening, and now they have the context. So anybody can ask question, okay, like what's happening, can you explain, and the agent would do that. So again, like with fewer people you are able to do a lot more and a lot faster.
Okay,
And
thank you.
that's just for this context. There, of course, there are a lot of other things that AI is proven to be very powerful, especially like creating data visualizations, simple front end apps, that you can like very easily code and now see all this data.
Thank you.
Thank you for your interesting presentation. I'm from PTTEP and I'm a driller,
Okay.
just like the other guy. Yeah, from your uh, presentation, it looks like the performance of the model depends a lot on the quality of the roadmap,
Yeah.
right? That we
Yes.
give
That
them,
is the key thing. Yeah.
right? And the roadmap, I mean, in this context, is a geological roadmap.
Yes.
One of the challenge that a dealer like us facing every day is that the geological roadmap itself is not certain,
Mm.
right? They tell us something to drill, and when our bit hit the ground, it's completely different,
Mm-hmm.
right? Which means the roadmap is not what it's supposed to be,
Mm-hmm.
right? In this, for human being, we have some sense of adjust it, right? But for your model, like I think one of the students asked, with 50 wells,
Yeah.
right? Model from that 50 wells with 50 roadmaps
Mm-hmm.
and 50 actual, right? When you face another roadmap, which maybe 50% off,
Yeah.
and your model might probably thinking on the basis of what it was trained. Just like a student, they are learning from 20 questions from the university, and they have thought, their frame of thought based on that,
Yeah.
right? When they see something new, that might, you know, take some time to learn. And I wonder how your algorithm, how your model can handle that in a fraction of seconds. Thank you.
Yeah. Thank you for the question. So, as I showed in the input models, we use these set of engineered features called lagged parameters. So, for example, lagged MSC, which is the mechanical specific energy. So, every time there is a change in formation, there would be a change in the trend for MSC as well. So that provides information, and it's a lagged particular, like it gives a snapshot of recent drilling that goes into the model to tell how it needs to change the predictions. So that's how it's able to keep up in real time. And then there is an automated calibration factor as well, which looks at the real time data and actual data and predicted data. And if there is some deviation, then it tries to correct the model in real time.
And if does it have the capacity to say something like if it is off by a certain degree, it can alarm us and say,
Yes.
hey, let's call geologist and see if the roadmap is still there. Can it have that, or it just blind going on with the assumption that it is correct without telling the driller?
So there is, so if we have these checks that for example, if the model the set points have suddenly shifted by a certain threshold, say by 30%, then something is off. Either the model is off, or the, like, not working as expected, because you don't want such drastic changes in your set points, right? So then it would go to like a, or like it would send an alert, and it would also go to a backup data where it would just send for example, P90 of ROP set point, and the max values that have been set, for example, max weight on bit. It depends on, so there are different settings for that, what they want to do for fallback. Like they could have a specific entries, for example, the like weight on bit should be this particular number. So just for that time, it uses that backup until the model is back, and it sends us an alert as well to look into. And initially we used to have more incidents like that, but over time, like we have done so many iterations that now it is more like runs in the autopilot without any significant issues.
Okay. Last question.
Yeah.
Sorry.
No problem.
Well, last question. What is your definition of the optimum ROP? Because I kind of agree with the earlier question that he challenged that with any set of parameters
Mhm.
that you think it give the optimum ROP, I can increase a bit of
Yeah.
something,
Yeah.
and the ROP will be better.
Mhm.
So the question is how you define
Yeah.
optimum ROP.
Yeah. So,
Thank you.
for example, there are two, what we, from our experience, there are two modes of drilling that drillers want to drill with. So, one is the wait on bit mode, where you want to drill with this wait on bit for, like, you want to use this much wait on bit in any condition, like that. You don't want to leave any wait on bit on the table. So, the optimum would be um, the basically you want to have the end game is to control the auto driller set points, right? So you want to give these set points where you want to have like do a headroom management for the auto driller limits and your set points, so that there is no conflict in the parameters. So if weight on bit should be in control, then weight on bit should be the set point that is the primary parameter which is in control, and the machine learning model is used to find that ROP, which would ROP set point that would give us that weight on bit without causing a diff pressure induced auto driller dysfunction, for example. And also, if there is have been a high stick slip, high vibration, then you have to manage your ROP set. So ROP optimization is not just max ROP; it's just how you want to drill. You determine those parameters using this like algorithm and data. And then there are some operators who want to drill with ROP control, like they want smooth ROP because that's like this most stable drilling state. And for that, like you want to the your weight on bit set point should be just a little bit below the max weight on bit, so that you leave a little bit headroom for the weight on bit set point, so that ROP is in control, but you are very close, so you are using the weight on bit that's available. So it's so those are the two drilling modes that we have been using. And in the US it's mostly the weight on bit control mode, and Argentina is the ROP control mode that they prefer. So, sorry, I thought I don't know if that was too technical, but
All right. I think it should be the last questions because we can keep up with time. But of course, she flew all the way from Houston here. She will stay with us after this, and then you can continue to ask her the questions. All right. So, on behalf of SPE Thailand, may I invite Kun Anupong Trailer to provide the token of appreciation for our speaker this evening.
No, in front, in front. Yeah, the cat, the cat.
thank you. Thank you so much.
Okay. Thank you, Ms. Kissy, for the very interesting presentation for our distinguished lecturer. And please stay with me for some few closing remarks. Okay, for the upcoming event for the SPE, we're gonna have the next monthly technical meeting on 19th of March, and we're gonna have a Songkran break in April, and we will continue our monthly technical meeting on 21st of May. So SPE have a referral program. So you will gain a free membership for the recruitment effort. As shown in the slide here, here is a reward for the SPE referral program, and another thing is a SPE patron program. So if you can refer 5 member gonna have 1 year free of membership. And here are all the showing slides. So these two programs will run together as a referral program and patron program. So for our network SPWLA Bangkok chapter, they're gonna have a technical meeting next week on Thursday, 26th of February. Yeah, at Jasmine Hotel, yeah, nearby here. And for the SPE Singapore, they're gonna celebrate their 50 years of the SPE community section. So it would be great if we can join us at the Singapore on 6th of April. So there are a lot of activity in the SPE Asia Pacific. So you can check it out on the website. But worth to mention that we're gonna have a OTC Asia in March in KL next month, and IPTC will come back to Bangkok, Thailand in 2027. So there are several channels that you can keep connect with SPE Thailand section at spethailand.org, and also we have the Facebook, LinkedIn, and Line official account. So you can just scan all these QR code and keep connect with us. And now we also have a YouTube channel that you can we can record all the technical sharing session here for the one who cannot join in the face-to-face monthly technical meeting. And this is very good venue for us. Also, we can exchange the knowledge and keep the record in the system. So you can check it out in the SPE Thailand YouTube channel. And last but not least, will be the lucky draw. We have special gift from SPE Thailand section. And may I invite Miss Kriti to give the lucky draw for 2 lucky persons.
How many?
One first. Anyone else can read?
You can butcher the name.
Okay. I'm having difficulty. Can you read?
นัทวินวะ
นัชวินไหมครับ T นามสกุลด้วย T WF Waterford โอเค
I did. Yes. Okay. Yes. Yeah.
One more.
Okay, one more. We'll see if we can read this time.
Ben. I can read this. Ben. Big lab. Biggest lab?
Thank you very much, Kriti.
Okay, lastly, please give a loud applause to the sponsor for the SPE Thailand technical meeting. And I think that that's all for tonight. Thank you very much for coming out tonight. Oh, sorry. So we can keep networking after the event. We have the promotion for 2 for 1 at the lobby bar at the ground floor in this hotel. So we can keep connect after the meeting for the one who want. And I think that's all for today. Thank you very much for coming and have a good night.
Thank you. Okay.